another device that we're going to look at briefly is called the capacitor. Okay, and the capacitor often comes with things that need timing or they'll take some time to do. So alarm clocks and things like that, anything that you need to set a time for things to happen, it usually involves capacitors. Okay, so a capacitor stores electric charge, but it takes a bit of time to store that charge. And it's a bit like a bucket if you look at a water dripping out a tap and filling a bucket. Okay, so a capacitor is the bucket, and eventually it will store all the water that's dripping out the tap, but it takes a little bit of time to fill. Okay, so a simple capacitor is basically made from two metal plates with a bit of insulating layer between them. And some have a polarity, so they have to be connected the correct way around. If they're connected back to front, they will be damaged. So the circuit symbol for a capacitor is usually just two lines next to each other, but you sometimes get a plus sign, which shows you which way around to connect them. Capacitance is measured in farads, capital F, but a farad is huge, so usually you see them being measured in microfarads or picofarads even. So micro, remember, is times 10 to the minus 6, and pico is times 10 to the minus 9. Okay, so if you connect a capacitor to a DC supply charge, so a battery or a cell, the charge is pushed around the circuit onto its plates. And when the charge gets to the plates, some gets left on the plates and stays there. So basically, some remain on the plates and some carry on going. And then each time the charge goes round, more and more build up on the plates. Okay, so you can see the diagrams here. The first diagram, we've got lots of electrons flowing, and only a few of them have been deposited on the plate. In the second diagram, we've got fewer electrons flowing because some more of them have ended up on the plate. And in the final diagram, this is when the capacitor is fully charged, so that bucket is full. All of the electrons have then built up on the plate, and we've got nothing left to flow around the circuit. So it takes some time for those electrons to deposit on the plate, to stick on the plate, and for there to be no more flowing in the circuit. But eventually, that capacitor fills up with charge. It's completely charged. Okay. So, as more charge is stored on the plates, less charge is flowing around the circuits. Okay, and eventually, the charge on the capacitor equals the voltage of the supply voltage. Okay, so and there'd be no electrons flowing around. So that capacitor starts off with 0 volts across it, and as the charge builds up, it gets more and more voltage across it until eventually it equals the supply voltage. And capacitors can be used as electronic input devices when part of a potential divider. So again, you can use these in circuits just like we use thermistors, we use light-dependent resistors, switches and things like that. You can use them in the same kind of way. But capacitors tend to take a little bit of time to charge up, so that's why they are used in time circuits. So another experiment, again I'll show you the video of the experiment later, is what we have a resistor and a capacitor in series with each other. You don't really need to worry about the push switch here, that's just so we can discharge the capacitor relatively easily. The important thing is we're measuring the voltage across the capacitor. Okay. So what we do with this experiment is we charge the capacitor, and we want to time how long it takes for the capacitor to get to the full voltage. So the full voltage will be the supply voltage. So remember we said it takes a bit of time. So it'll start off with 0 volts to go to 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volts. So it will take some time for that capacitor to get fully charged. And we want to know how long will it take for the capacitor to get fully charged for that voltmeter reading to become 6 volts. Okay. So we use various different, with this experiment, we change the resistor and we change the capacitor, and we see how that affects it. So I've got some results here, and you'll see that if you increase the capacitor, so if we compare this one and this one, okay, the resistor stays the same, but the capacitance is increasing. That shows you that actually the time taken for it to become fully charged also increases. And the way I think about that is, if you increase the capacitor, you're increasing the size of the bucket. So, of course, if the drip's just the same, then it will take longer to fill a bigger bucket, won't it? So the time taken for the capacitor to charge increases because the time taken to fill a bigger bucket increases. With the resistance will also change the time it takes to charge. So if we look at this one and this one now, bottom two, you can see that the capacitor stays the same, but we've decreased the resistance. Okay, now the resistance affects how quickly we can flow, the current can flow. So the higher the resistance, the slower the flow. Okay, so if you increase the size of the resistor, it will be a slower drip from the tap. So it will increase the time it takes for that bucket to fill. So in conclusion, increasing the size of the capacitor increases the charging time, and increasing the size of the resistor will also increase the charging time. So that conclusion is what you need to know for this, using capacitors and resistors in circuits. Okay, so I'm going to stop there and let you watch